Welcome. Let's start at the beginning. This is lecture 1. We're going to talk about numbers in algebra. This is a course in number theory, and so I suppose the first order of business is just to set some terms here. First of all, we use this n for the natural numbers, like 1, 2, 3, 4, etc., etc. The integers are natural numbers with their negatives and also 0, so these are integers. The Z is actually from Zahlen, which means number in German, which I'm mispronouncing. Then you have rational numbers, aka fractions, and so there you can build rational numbers from integers. You take one integer over another, and we assume that of course the denominator is non-zero. And then next level, you've got the real numbers, right? Real numbers are, well, they form the number line. That's what we'd say here to start with, sometimes called the continuum. And then, of course, past the real numbers, you've got your complex numbers, all right? So in number theory, a lot of the time we're spending really analyzing natural numbers, specifically questions about primes and properties of primes and so forth. But we're also interested in things beyond primes. So sometimes it turns out that to understand primes, you do well to look at certain kinds of complex numbers even. And looking at those other number systems reveals properties of primes. We'll see that later this term as we study the Gaussian integers, okay, for example, which are a particular kind of complex number. Let me just share some fun facts with you here before we go on. So it's interesting to notice that the cardinality of n, z, and q is all the same. These are all the same size. There's a one-to-one and onto mapping, a bijection, a one-to-one correspondence between the natural numbers, between the integers, and between the rational numbers. So this is kind of surprising because it seems like the rational numbers are a lot bigger, but actually not. And then also perhaps interesting is that there is a one-to-one correspondence between real numbers and complex numbers. Real numbers and complex numbers also have the same cardinality, but that is different, of course, than the cardinality of n, z, and q. So n, z, and q, these are what are called countable sets, whereas the real numbers and the complex numbers are uncountable. Now, that concept of size, cardinality, really doesn't have too much to do with this course, but I mention it for your information. Now, even though the first three of these sets have, and so I guess maybe I owe you a notation. So if we use this for cardinality, so we could say the cardinality of n is equal to the cardinality of z is equal to the cardinality of q. These are all countable. Whereas the cardinality of the reals is equal to the cardinality of the complex numbers, and that is not equal to the cardinality of the natural numbers. So these guys are an example of an uncountable set. Okay. Anyway, that's the part of a much longer story about cardinality and all that. That's pretty much all I'm going to say in this course about that, actually. So these have that in common, and these two have that in common, and yet all five of these are really quite different. All right, let me just talk about their structure a little bit. So let's see here. Natural numbers, well, if we add two natural numbers together, we get another natural number, right? So natural numbers are closed under addition, right? Now that addition is commutative, it's associative, right? The integers, but on the other hand, the natural numbers don't have a concept of zero, right? There's no additive identity in here. 0, if we add 0 to any integer, we get that integer back again, right? So there's a 0 in here, an additive identity as it's called. And the integers are closed under negation, right? There's negatives for each number. Again, the addition is associative, it's commutative, it obeys the usual laws of distribution, the usual distributive laws and all that, right? Now, rational numbers are interesting because there's something that we could do with integers, and even with natural numbers, right? You can multiply natural numbers and get a natural number. You can multiply integers and get an integer, right? However, there's no way you can get like a multiplicative inverse of a half, of 2 rather, in the integers, right? Because 1/2 is the multiplicative inverse, and 1/2 is not in z, right? But this q has the interesting property that every non-zero number has a multiplicative inverse. So that's very interesting, and that is what makes q what's called a field. All right. So q, r, and c, these are fields, right? And that means that every non-zero number has multiplicative inverse. All right. However, the rational numbers and the real numbers and the complex numbers are still very different in their structure. Let me just talk a little bit about that. So, what's the thing? What makes q special? Q is not what's called complete. To say a space is complete means that every Cauchy sequence in that space converges to a limit point inside that space. So the quintessential example showing that the rational numbers are not complete, well, that's easy enough. You take something like the digits of the square root of 2, right? So let me put that down here. So like the square root of 2 is what? 1 point, well, here, just a second. Let me cheat. Let's see here. Square root of 2. Oh, well, that was unhelpful. All right, there we go. 1, and then 1.4, and then 1.41, and then 1.414, and so forth, right? So these are the truncated decimal expansions of the square root of 2, all right? So here, let me make sure you can see it. All right. And so at each stage here, this is a rational number, right? Because that's 14 over 10, that's 141 over 100, that's 1,414 over 1,000, right? So this is a sequence of rational numbers, and yet the limit of this is the square root of 2. And you can prove that the square root of 2 is not rational, right? So the square root of 2 is what we call irrational, all right? In fact, we'll have a whole lecture just on that one fact, all right? So that's what I would say is the rational numbers, they form a field, but there's something missing in terms of analysis, right? If you try to do calculus over the rational numbers, you get into trouble. You don't have you don't have the intermediate value theorem. They're kind of like holes in it, so to speak. Now the real numbers. What's the problem with the real numbers? Well, real numbers, it is complete, all right? And towards the end of this lecture, I'll talk more about how exactly, I'll actually talk a little bit about how you would build these, specifically from some constructions, right? So at the end of this lecture, we'll come back to how to build these formally. So R is complete, and yet, not all polynomials factor, or another way you could look at it is there are polynomial equations which don't have solutions. So quintessential example of that, just I keep it real simple here. x squared plus 1, right? You cannot factor that over the reals, right? Because what do you need? You need x squared minus I squared, where I is equal to the minus square root of minus 1, so like I squared is minus 1. And then you can factor. See, that's x minus I times x plus I. As you can see, what have I done? I've used the next thing up the chain, right? Complex numbers. So complex numbers, they're also complete, just like the real numbers are complete. And any polynomial factors completely. That's a different use of the word complete. Sorry about that. So like, you know, that's the fundamental theorem of algebra. Every complex polynomial has a 0. And once you have that, that means you can factor them completely, right? So this, both the real numbers and the rational numbers are also different than the complex numbers in the sense that they have an inequality, right? They're ordered. There's a nice ordering which plays well with the multiplication and the addition in these spaces. So like Q and R have a less than and greater than. In contrast, complex numbers, not so much. Okay, so that's the starting. Now, let me talk about this. So number theory, largely speaking, is divided into sort of two. Let me just add a little bit more here. So one of the things we'll look at is how to solve equations over n or z. So those are called Diophantine equations. And then the other thing I should mention here at the start is when we think about number theory, there's really two sort of camps, if you will, major directions. There are algebraic number theorists, or you could say algebraic number theory. You thought that was a hashtag. It's not. It's a number. Algebraic number theory, and then there's analytic number theory. So, and so, you know, to be fair, these are not really mutually exclusive categories. These divisions we make in mathematics, they're never quite as rigid as students make them out to be. The picture is probably more like this, you know. There's definitely some overlap. That's probably still the wrong picture. But just as a point of going forward and just kind of giving you a picture of the course really quickly here, we're mostly focused on the algebraic side of things because analytic number theory it tends to be a little bit more advanced, I would say. And we also need tools from analysis, which we don't know if we have, right? So like I assume you guys know some calculus and maybe a little bit of linear algebra on occasion. Certainly basic algebra, I think you know. But you know, the real highfalutin analytic number theory requires pretty deep and working knowledge of complex analysis and things from beyond that. So that's a little bit above our pay grade in here, right? On the other hand, algebraic number theory, a lot of the arguments from algebraic number theory are actually quite accessible to students of many levels. So we'll focus more on here. And so my first sort of example of algebraic number theory is just with Pythagorean triples. All right, so in fact, this first couple lectures, we're really not doing too much number theory. We're more focused just on basics, just to get us started here, right? So Pythagorean triples. Well, first of all, a little bit of history. How old is the problem of Pythagorean triples? So here's, this is not our book, I suppose, but it's a nice book. And let's see here, look at the timeline. Ooh. Classical period, huh? Pythagoras, 569 to 500 BC. Whew, that's a little old. So those kind of Pythagorean triples, but I think if you take a look at the history of these sorts of problems, they were known to the Babylonians and to pretty much all the ancient societies. that we have records of, they are all studying right triangle trigonometry because, well, they want to build stuff, right? So what is a Pythagorean triple? So let's focus our attention on that for a minute. A Pythagorean triple is three natural numbers which have the relation a squared plus b squared equals to c squared, right? So that means that there's like a natural correspondence between these triples and particular triangles, right? So you could think of a given triple as like the blue triangle, right? The inside one, let's say, right? And if you think about that, you could like rescale it, right? You could just like multiply this triangle by some positive constant lambda, and you could make a bigger triangle, right? Just by like, say, doubling this lengths of the sides or quadrupling or whatever. And so geometrically that's clear, you could do that, right? Similar triangles. But it's also clear from the Pythagorean theorem that if a squared plus b squared is equal to c squared, then lambda a quantity squared plus lambda b quantity squared plus lambda c quantity squared is equal to, well, the same equation, right? So what does that mean? That means that if we have one triple, ABC, we can get another one, lambda a comma lambda b comma lambda c. For example, 3, 4, 5 is a Pythagorean triple. It's easy enough to check. 9 plus 16 is 25, which is 5 squared, right? What is less obvious is that if you multiply by 8, right? 8 times 3, 4, 5, namely 24, 32, 40. Here, if you don't believe me, let's check my handy dandy calculator here. 24 squared plus 32 squared equals 1600. Hey, check that out. And of course that is 40, square root of 40 squared. So if you have one Pythagorean triple, you can generate all kinds of new ones, right? And well, there's tons more to say about Pythagorean triples, so I just wanted to give you a short little example of algebraic number theory in action, right? So here we've used some algebra to discover, how to get from, one sort of number theoretic thing, a Pythagorean triple, to another, right? So not a terribly impressive example, I think, but anyway, just to get us started. All right, so that said, let us go on to the next topic here, which is equivalence relations. So in order to understand the end of this lecture, we're going to really need to understand a little bit about equivalence relations. And I hope this isn't your first time hearing about them, but maybe it's been a while since you thought about them, so let's review. An equivalence relation on a given set is some kind of rule, right? Let's say tilde, or I'm going to call that similar. You know what? I'll call it squiggle. There we go. Squiggle, which is 1, 2, and 3, reflexive, symmetric, and transitive. So reflexive means that x is related to x for all x in the set. Symmetric means that if x is related to y, then y is related to x. Transitive, of course, means that if x is related to y and y is related to z, that implies x is related to z. So this gives us what's called an equivalence relation. So many things we do in mathematics are really equivalence relations. So many things. So the equivalence class is also important. This is the set of things which is equivalent to a given thing. So here x is called the representative of the class. I should probably write that down. So this is the equivalence class with representative x. All right, because the x is here. Now, is that unique? Certainly not, right? There are many different representatives for a given equivalence class, typically. So here's just a really simple example. If we take the set of integers, then we could define an equivalence relation by saying x is related to y if they're of the same parity. All right, so in other words, if both x and y are even, they're related, or if both x and y are odd, they're related. So in this setup, the equivalence class of 1 would just be all the odd integers, all right, which we could denote 1 plus 2z, right? And the equivalence class of 2 would just be all even integers, like so, right? And you can check that this definition of equivalence satisfies reflexive, symmetric, and transitive. It's kind of silly. There's really not much to check here. So, all right. And this illustrates something, which is that the equivalence classes of a equivalence relation will partition the set on which it forms an equivalence, right? It will divide the set up into disjoint pieces. So like the way I could say that here in terms of an equation, the partition I'm talking about is that the integers are equal to the even integers, right? Union with the odd integers, which I could either write 2z plus 1 or I could write 1 plus 2z. It really, it's up to you whether you want to write the plus 1 before or after. The addition is commutative here, so it doesn't really make a difference. And of course, so by these I mean this is that set right here, and this is this set right here. These are disjoint sets which cover the whole of the integers. It's a partition. All right, so actually this is important, so we should make a definition. Integer x is even if there exists another integer k such that x is equal to 2k. An integer x is odd if and only if, this is what IFF means, if and only if, there exists k in the integers such that x is equal to 2k plus 1, right? So we need to know these definitions. I'm going to ask you to prove some things with those definitions. You must use those definitions for such proofs. I think it's only fair to give you an example of such proof, so here it is. Proof example. Prove the product of an even and an odd integer is even. All right, great. So, so suppose integer x is even and y is odd, right? Then there exists j and k in the integers for which x is equal to 2k since x is even, and y is equal to 2j since y is odd, right? By the definition of even odd respective. Consider then x times y is equal to 2k times 2j plus 1, right? But then by algebra, factor the 2 out, we've got 2 times 2kj plus k. But hey, 2kj plus k is an integer, so we find that xy is an element of 2z because it's twice times an integer, right? Thus, xy is even. And this is just my own personal notation. I use that. That means end of proof for me. So, all right. So, anyway, we need to. I think I've asked you a homework problem or two about proving things are even and odd. So I wanted to review that with you guys. All right. So next up, let's talk a little bit more about algebra. So, one of the interesting things to know about, mathematicians is that it wasn't so long ago that mathematicians looked dimly on like negative numbers, and I think it's really hard to appreciate from our modern perspective why negative numbers were sort of ignored as solutions to polynomial equations. So I think this little exercise here is very helpful in that it helps you understand the mindset of some of the medieval mathematicians who had that idea. So let's look at it. This is why completing the square is called completing the square. So we're setting out to solve x squared plus 26x equal to 27, all right? And so the idea here is basically to make a little square, all right? I'll just freehand it here. You guys don't care if my x is messy, do you? So here's x, an x by x box, right? And then 26x, well, that's what? You can take this and you can make a, not to scale obviously, right guys? So this would be 26, and this would be x. So the area of x squared plus 26x could be represented by this figure, right? If we think of x squared plus 26x as an area, it's these two figures together, right? But you could replace these two figures with what? You could keep your x by x, right? Take this, cut it in two, and if you cut that in two, we get 13, and of course this is still x, right? And then we got another one. I'll flip it, put it down here like this, all right? And so 13x, all right? And then you can see, well, to complete the square, what do? We go So we have to do what? We have to add in this piece, this chunk right in here, right? Which would be what? 13 by 13, right? So we know that the area of this one was 27 by assumption, right? So this has area what? 27 plus what? Plus the area of this new fangled square we just added, right? So 13 times 13, 169. Now 27 plus 169 is, what is it? I think it's 196, but let me check. 27 plus 169, 196. All right, and that is 14 squared, I believe. Yep, 14. Aha. So this has area 14 squared, right? And since this is a square, it must mean that we're looking at the 14 by 14 square, right? Overall. So that was, I'm trying to make it the same size as that. I've obviously failed. But, so what does this tell us? You're like, oh, wait a minute. Aha. So you're like, aha, I have a thought, right? So x plus 13 must be equal to 14, right? I mean, you could look at, like, say this side right here, right? And compare it to this side over here, right? Same square. So what's that tell me? X is equal to 1. Aha. So if this is how you think about a quadratic equation, do you see why you wouldn't allow x to be negative? See, it would be completely counter to the whole idea of the equation. Because see that for the medieval mathematicians, people back in, like, say, 1,000 to 1,500, somewhere in there, give or take, and before, these kinds of equations were really just a notation for the corresponding geometry problem. And so, yeah, I mean, you reject negative solutions because that's not what this equation means, right? The equation really means this. But in our modern parlance, that's not a word, is it? Anyway, in our modern way of thinking, we think of the equation first, and we've completely forgotten about this picture, right? This is why completing the square is completing the square. Now, the other thing I think to think about in terms of ancient mathematicians, it's important to keep in mind the notation we're using is relatively modern. So here's a quote from Journey into Mathematics, Introduction to Proofs by Joseph Rotman. Rotman's writings are really wonderful. Anyway, here's the quote on page 57. Here's a problem from the 9 chapters on mathematical art written in China about 2,000 years ago. Here it is. There is a door whose height and width are unknown, and a pole whose length is also unknown. Carried horizontally, the pole does not fit by, I don't know, vertically, and it does not fit by slantwise. It fits exactly. I'm missing something about that typesetting. Sorry, guys. What are the height, width, and diagonal of the door? All right, so you notice that there's no equation, right? Everything is in terms of prose, in terms of sentences, and this is also true, of course, of other, I mean, it's true in China, it's true in ancient Europe, it's true in ancient India, it's everywhere where math was done. There was, well, up until algebra was invented, up until this symbolic way of thinking, we had to do things in sentences, right? Completing the square, just as a point of order here, I think I should actually take a second here to review completing the square, because I think not everybody knows actually, and I think it's worth our time. So let me talk about completing the square instead of just geometrically. Let me talk about it in terms of polynomial algebra. All right. So how do we complete the square? Let me just do 3 examples for you, just to try to show you why I think it's really important to know about this. So let's see here, example 1. I'll do exactly the one we just did geometrically, but this time I'll do it algebraically. X squared plus 26x, and I'll move the 27 to the other side, minus 27 equal to 0. All right, so completing the square. We have x plus 13, so you take half of whatever's the coefficient here, you square it, right? Then to be fair, that's adding 169, so I have to subtract 169, right? But then we have to recognize, okay, so what that is x plus 13 squared minus 196, right? But I'm just going to go ahead and get straight to the point. That's 14 squared. All right, so at this point, we notice that we've got a squared minus b squared, right? So by the difference of squares, this is x plus 13 minus 14, x plus 13 plus 14, right? So what do we have? We've got x minus 1 times x plus 27. So this okay, so then by the factor theorem, or whatever you want to say, the solutions then are x equals to 1. And the other solution that the medieval folks would ignore, minus 27. So that's completing the square. Now, you're like, well, I could have just factored this, right? Well, that's true. You probably could have just factored this, right? But completing the square takes the guesswork out of it. Let's do another example. So let's see here, example 2. Let's see, could you factor, let's see here, how about this? 2x squared plus 7x plus 1, right? And I'm not going to look at this as an equation, I'm going to look at this as an expression, right? Because you should notice that completing the square doesn't just allow you to solve equations, it allows you to factor. Let's see how this goes. So my first order of business is to factor out that pesky 2. So this is 2 times x squared plus 7 halves x plus 1 half. All right, great. Now, up next, I'm going to leave that 2 out there. And what's half of 7 halves? Well, it's 7 quarters. So I do x plus 7 quarters quantity squared. Right? And then to be fair, I've got to subtract 49 over 16. Let's be smart about this. That 1 half, how many 16ths is that? Well, that's, I believe that would be 8 16ths. Right? All right, so what do we got? We've got 2 x plus 7 over 4 quantity squared. And let's see here, that's minus 41 over 16, so that is minus the square root of 41 over quantity 4 squared. Now it's a little tricky what I just did, but my point is you want to look at that as something squared. We're always using the difference of squares formula. So now I've got, difference of squares, so I got 2 times x plus 7 quarters minus the square root of 41 over 4, x plus 7 quarters plus the square root of 41 over 4. Now, this right here, my friends, I don't think you would have been able to guess that's how you factor that, right? But completing the square gives us a ironclad, you can't go wrong method. Completing the square doesn't involve guessing. Completing the square is an algorithm. All right, so one more here. Example 3. One of my favorite examples. Let's see here. X squared plus 4x plus 5. All right, so we take half of the coefficient of 4. That's 2. X plus 2 squared, right? Then we have to subtract 4 to be fair. Add 5. So what that gives us, of course, is x plus 2 squared plus 1. So if we were only working with real numbers, that would be it. We'd be done. We can't factor that, right? When you complete the square, you can see what kind of quadratic you're dealing with. When you complete the square, if you get a negative thing after simplifying, then that speaks to the fact the difference of squares formula allows you to factor, right? But if you don't get a negative, then you're stuck with it. That's what's called a prime or an irreducible polynomial. However, if we allow ourselves complex numbers, then we can convert anything like this into an imaginary number squared. See, so that's just x plus 2 squared minus I squared, all right? Which then, again, difference of squares, x plus 2 minus I, x plus 2 plus I. So there you go. Completing the square in a nutshell. There it is. All right, so now that I've given you a little refresher here into some ideas of mathematical proofs and definitions, let's go back to the start and talk a little bit more about how would we actually define these number systems more carefully. See, because I really just did what? I just gave you some letters and a more critical person could say, well, okay, but how do you know these exist, right? And you're like, well, you don't have to worry about that. Let's just assume they exist. People have been talking about it to me since the days of my youth, so surely they exist. Well, okay, fine, but let's see how mathematicians know they exist, all right? So let me just walk you through it. So here they are. So let's start with the natural numbers. And I'll try to be quick here, because I don't want to take too much of your time, but zoom in a bit. All right, I think that's about as far as I can get in. So the natural numbers were understood rigorously for the first time in the 19th century in terms of what are called the Peano axioms. And so here they are. 1 is a natural number. Every natural number has a successor. 1 is not the successor of any natural number. If the successor of x equals the successor of y, then x equals to y, and then you've got induction. So we'll talk a lot more about induction in lecture 2. But, so how do you actually construct natural numbers? Well, there is a way to do it using set theory. Here's how it goes. So the story goes like this. You let the empty set model 0, then you define the successor function being x union the set containing x. So then you make 1 the successor of 0, so the successor of the empty set is the empty set union the set containing the empty set, which is just the empty set again, because there's nothing in the empty set. And then 2 looks like this, and then 3 looks like this. So you have sets of sets of sets of sets. Okay, and just anyway, because let me just read through this. It's kind of fun. This is how you can build the numbers 1, 2, 3, and so forth from just sets. Like 1 is the set containing 0, 2 is the set containing 0 and 1, 3 is the set containing 0, 1, and 2. If you just sort through all this stuff up here, and as such you can define addition and multiplication in this world of thinking in terms of the successor function, right? And so this construction is due to von Neumann, who did some really deep work in mathematics and also I believe computer science. But anyway, this is a model of the natural numbers in terms of set theory. So if you come around, if you're teaching some student and you're like, there's no such thing as natural numbers, you'd be like, well, if you believe in such a thing as a set, Here's how you make natural numbers. Now, this is not actually how I think of natural numbers, right? I just think of natural numbers like this: 1, 2, 3, 4. You know, but I only got 10 fingers too, so it's kind of limited. Anyway, so here's some easy homework problems you could prove on these things. So x less than y and y less than z implies x less than z. So I've defined x less than y up here to be x is a subset of y, right? So if you know properties of subsets, right, x is a subset of y and y is a subset of z, well, that implies that x is a subset of z, so that gives you a, right? And this would mean x is a subset of y, this would mean y is a subset of x, right? So if you have double containment, you get equality, right? How do we prove two sets are equal? We prove one's a subset of the other and the other is a subset of the one. So there's that. And then to show that 1 times x is x, again, that is going to require the use of induction. So the part C you have to think about a bit, but part A and B here are actually not too hard. So that's it for natural numbers. All right. So what's up next? Now, what is a natural number? You say, well, are natural numbers really the empty set and then union with the empty set? Well, I wouldn't say that. I would say that what I just showed you is a model of the natural numbers. The natural numbers really are better defined by the inductive property. It's a set that has the inductive property and so forth. But anyway, so then next up, how do you get the integers? Well, you can define integers by basically saying that using this equivalence relation. So the pair a comma b is a model of a minus b, and so like if a minus b is equal to c minus d, that would be the case when. Just write down here for a second. So check that out, right? So if a minus b is equal to c minus d, that would you'd need for a plus d is equal to b plus c. So the game that's being played here is how do you get at subtraction, right? By just using addition. Well, this is how you do it. And this is very sneaky, a pretty sneaky construction here, but you can define, so that defines an equivalence relation on the Cartesian product of the integer of the natural numbers with itself, and so that that n sub 0 mod this equivalence relation, as they say, is a model of the integers. So anyway, you can define addition and you can define multiplication like here and here, and that if you can sort through that, then you can see that in fact this gives us a way to construct the integers, all right, using these equivalence classes. Let's see here. To show, well, anyway, this is a good homework problem to work through. I'll just leave it at that since time is limited here. Problem, rather, next up, so you got natural numbers, then you got integers. What's up next? Well, rational numbers. So to get rational numbers from integers, you can build something called the field of fractions. So beginning with integers, you define equivalence classes x comma you define an equivalence on pairs of integers as this. Really, the idea here is to think of x comma y as a model of the fraction x over y. And so how would we have two fractions are equal, a over b is equal to c over d, if when you cross multiply, you've got ad is equal to bc, right? So of course there's many equivalent fractions for a given one, like a half is equal to 2/4 is equal to 3/6 is equal to 500. There's infinitely many of these, right? So to capture this formally, we have a comma b is equivalent to c comma d if and only if ad is equal to bc. All right. You can prove this is an equivalence relation on S here. All right. And I said S was z cross z. That's not quite accurate because it's the pairs such that the second one is non-zero, right? So S is a subset of z cross z, but it's not equal to z cross z, right? So this is a subset of z cross z. Again, because the second component can't be 0. Anyway, so we define a fraction to be like this. A over b, it's all pairs c over d and s such that it's equivalent to a b is equivalent to cd. And then you can define addition and multiplication of fractions in this way. Now I say show addition is an S mod, the equivalence relation is well defined. What that means is you'd have to show that if you picked a different representative for the class, you'd still get, you'd still get the same result. So let me show you multiplication. I'll show you multiplication is well defined. I think if you can see that, maybe you can figure out how to do addition well defined. So just to be clear, I'm asking a question here. Let's see here. So we want, suppose a over b is equal to a prime over b prime, and x over y is equal to x prime over y prime. In other words, I'm looking at two different representatives for the same fraction, right? So then consider a over b prime times x prime over y prime is equal to what? It is equal to, by definition, a prime x prime over, can you see me writing, or am I off the, oh, I'm sorry, I was beyond the universe. My bad. My apologies. Let me zoom out a bit here. Sorry about that. Oh, by the way, the secret word is juggernaut. That's J-U-G-G-E-R-N-A-U-T, juggernaut. So a prime x prime over b y prime, b prime y prime. Don't be deceived, this is a notation for, well anyway, let me shut up. So, great, and yet a over b times x over y is equal to ax over by. So the question is this and that equal? Notice ab prime is equal to ba prime, since a over b is equal to a prime over b prime, and xy prime is equal to yx prime, since x over y is equal to x prime over y prime. All right? So, all right, so then what? Consider so we're trying to show that this one and this one are the same fraction, right? Let me call this one 1 and this one 2. All right. So let's look at a prime x prime times by. All right. That is equal to, let me rewrite this as a prime b x prime y. All right. Now remember, we can trade a prime b for ab prime, and we can trade x prime y for xy prime, right? Because they're because we have these relations right here, right? And what do we have then? We've got ax times what? Times b prime y prime. And if you, hence 1 is equal to 2. See, because we've just shown that a prime x prime times by, right, is equal to b prime y prime times ax, which is what it takes for these fractions to be equal. All right, thus multiplication is well defined. So anytime we make a definition in terms of an equivalence relation, technically you need to show that that definition is independent of your choice of representative. All right? Okay, so anyway, just wanted to give you, an example of something, a proof that's similar to your part A there. Yeah. Now, showing multiplication is commutative and showing addition is associative, that should be relatively straightforward. So associative means what? That means that you have like A over B plus C over D plus X over Y equals to A over B plus C over D plus X over Y. Feel free to use different letters if you don't like these. And where you put the parentheses doesn't matter, right? You can either add these two first and then that one, or you can add these two first and then that one, right? So that's associative. Commutative, well, anyway, I think you hopefully know what that means. Problem 9. Actually, I hope you know what associative means, but anyway. Next up, the real numbers. So you got rational numbers. What's up next to the real numbers? So the construction of the real numbers is intrinsically analytical. There are three popular routes to construct the real numbers. You could look at the completion of the rational numbers with respect to the Euclidean metric. In other words, it's formed by adjoining the limit points of all Cauchy sequences of rational numbers. You could say the real numbers are formed by Dedekind cuts. Don't ask me what that is. That's a way of doing this Cauchy sequence thing with sets, and it's rather conniving. It's pretty sneaky. That's a mid 19th century, 1850s or whatever, in there, some kind of that time frame. And then, of course, the other thing, and this is how engineers tend to define real numbers. It's a set of numbers with decimal expansions, and I actually like this as a working definition for us and for the purpose of this problem here and this course at the moment, because it's the least technical. And also the most familiar, right? So, technically speaking, to prove claims I make about, sets of real numbers in terms of decimal expansions, that actually means I need to prove things about adding and multiplying series, these convergent series, which you could do. I'm not going to do that. We're not going to do that, okay? I just wanted to mention you could do that. But anyway, a real number is a number if it has a decimal expansion. And that means that you've got a finite number of digits to the left of the decimal point, right? And you can have as many as you like to the right, right? Of course, m can be billions, right? But it has to start somewhere. There is a highest power of 10 which appears in the number, right? And so this is our typical decimal notation, where we put the decimal point there to denote the difference between the positive and the negative powers of 10. And so, for example, if I had 123.456456, that means 100 plus 20 plus 3 plus 4/10 plus 5/100 plus 6/1000 plus 4/10,000, and so forth. And the neat thing here is, just to link back to, where do the rational numbers figure into all this? It turns out that the real numbers with eventually repeating decimal expansions are the real numbers, which are equivalent to rational numbers. This basically stems from the geometric series, which perhaps you should remember from Calculus 2, which says that, a plus ar squared plus which we could factor a out, and we get a over 1 minus r, provided that the absolute value of r is less than 1. So that's essentially the tool we need to see that. So, for example, if I've got 1,245 and 0.34555555 repeating, right? Then I can split off the part which doesn't repeat and the part which repeats. Of course, anything that's a truncated decimal like that, you can rewrite as a fraction by just doing the silly thing of getting rid of the decimal point and dividing by 100 here. And the other one, the 0.555 repeating, is 0.05, and then 0.0005, and so forth. which you can see that a here is 0.05, and then the radius, the ratio rather, is 1/10. And so by the geometric series result, you've got yourself a, let's see here, sorry if I was out of frame, my bad, 0.005 divided by 1 minus 1/10, which is the same as 5 over 1,000 times 10/9, because that's 9/10. And so you get 5 over 900, and then, of course, you can add the non-repeating part to the repeating part, and you get, there you go. So x, as you can see, is a fraction. There's nothing particularly special about this example, so I would invite you to see your way through it by finding the rational number that has decimal expansion with 348 repeating, right, 12.348, or the rational number with this decimal expansion. I think it repeats. I see 9.5. I think it's repeating. Let's see here. 238,095, 238,095, 238,095. Ah, yeah, so 238,095 is repeating here. So I don't think I really need to give you quite that much of it, but, you know, thank you, Wolfram Alpha. So, anyway, there's a fun one. And then finally, last at least, but certainly not the least of these examples, is the complex numbers. So it's funny, I think going from rational numbers to real numbers is by far the most complicated thing in the things I've shown you. I know if you haven't seen these constructions before, they're kind of like, what? But my point to you is, with a little bit of time and energy and a desire to be curious about these things, you can construct the basic number systems using some set theory and just undergraduate mathematics. I would say real numbers from rational numbers, maybe not quite so much. I mean, that was tricky. And real numbers are important, right? Because without real numbers, we don't have calculus. And, you know, it's interesting to note that the decimal expansion of real numbers, it only predates Newton by about 50 years. And, you know, if you think about it, that decimal expansion is so much of how you would do approximations. How would you do approximate calculations without decimal expansions? Think about it. It'd be really difficult just using rational numbers. But fortunately for Newton and the other mathematicians of his time, they had decimal expansions. But that was a relatively new technology, if you will. Complex numbers, in contrast, I think are pretty easy to construct. So this is sometimes credited to Gauss, sometimes credited to Argon, I think, of the Argon plane. Although I would say it really should probably be called the Euler plane, since he was doing these things back in the 1800s, honestly. Maybe not quite like this, but, you know, the notation I is from 1777 in Euler. Anyway, so for complex numbers, you can define them as just pairs of real numbers with a funny multiplication. And this funny multiplication has some really neat things. First of all, 1, 0 times xy is xy again. So that means that the pair 1, 0 is basically functioning like the number 1. In contrast, 0, 1 times 0, 1 is minus 1, 0, right? And that you could just as well look at as minus, 1, 0. And so that's like the number minus 1. And so, in other words, if we use the notation a plus bi, then part b of this problem is really showing you that I squared is minus 1. And essentially that, more to the point, the number I is modeled by the pair 0, 1. So with the plane and this funny multiplication, you can create complex numbers. Now there are other ways. You could look at 2 by 2 matrices of the form A minus B, BA. So 2 by 2 matrices like this are also, you know, you can identify them with A plus BI. And in this funny world, the I is like 0, minus 1, 1, 0. My point to you is just that there are many ways of building the complex number system. And in fact, there are many ways of building the other number systems I've shown you. The point of these constructions is not that these things are the constructions. The point is that it's possible. There are such systems with such properties, and it's worthwhile to study them, and that's what we'll do this term. So anyway, thanks guys. Sorry this went a little bit long. I'll try to make these shorter, generally speaking. So thanks.